Here we are going to talk about the linear quadtree as the last space-driven SAM that we are going to introduce in this course. So earlier we talked about the quadtree, and we know that one of the critical problem to the quadtree is that it is not a balanced tree, so that it will suffer from the skewed distribution of the data. So which means that some part of the tree will be deeper than another part of the tree, and as we know that the performance, the query performance will be different if the tree depths are different. So how to solve this problem? There is a solution which is called the linear quadtree. So it's basically a variation of Quadtree and proposed in 1998, and then it tries to solve the problem of skewed distribution to balance the Quadtree. So the key idea of this linear quadtree is to apply B plus tree to index the leaf nodes. Alright, so this is the key idea over here. So pay attention to this. Let me try to say it again. So basically, the key idea of the linear quadtree is to apply a B plus tree, which is the balanced tree, and we just directly use the B plus tree to index the leaf nodes of quadtree. To index the leaf nodes of the quadtree. So in this case, even with the skewed distribution that the quadtree is unbalanced, then in this case, because we only index the leaf node of the quadtree, so the query is conducted on the balanced B plus tree. So in this case, the query time only related to the depth of the B plus tree, and in this case, it's a balanced tree, so that it won't be affected by the skewed distribution of the data. But however, there's one big issue because the B plus tree only manages one-dimensional data and it's a sortable data. And so, but however, the quad tree it's two-dimensional. So it means that the linear quad tree require to convert the two-dimensional quad tree nodes to one-dimensional nodes. And how to do that? We are going to talk about one important mechanism or one important structure, which is called the space filling curve. So what exactly is the space filling curve? So basically, a space filling curve it defines a total order, or you can say a one-dimensional order on the cells of the two-dimensional grid. Alright, so basically, we have a two-dimensional grid, and we want to find a certain order on those two-dimensional grid or two-dimensional cells. So one key of this is to preserve one key is to preserve the two-dimensional proximity in the one-dimensional order, which means that if two cells they are close by with each other in the two-dimensional grid, then they should be close by to each other in the one-dimensional order as well, so that we can preserve these two-dimensional proximity characteristics in this space in this one-dimensional order. So the importance of doing this, importance of these is because when we search in the sorted nodes, that the nodes they are close in the two-dimensional space, they are close in the disk blocks. Because this disk block, the order of the data will be stored in the disk blocks according to this one-dimensional order from the space filling curve. So it may not be so easy to understand just by the description over here. So let's take a look at some examples. So there are two very famous space filling curves. One is called Z ordering, or Z order, which has been proposed like long time ago in 1966. So as you can see, the reason that is called Z order or Z ordering is because the order, it looks like the orders of the two-dimensional cells. It looks like the like alphabet Z. So it's like kind of like this order. So as you can see, if there's only 4 nodes over here, you can say 4 cells in this space, then the order is 0, 1, 2, and 3. So which means that the first node is this node. The second node is this one, and the third node is this one, and finally the final node is this one. So it looks like a Z character over here. And if it's a two-dimension, if it's you can say like 16 nodes or 16 cells divides the whole entire space, then the order will be 0, 0, 0, 1, 0, 2, 0, 3, and then connect to 1, 0, 1, 1, 1, 2, 1, 3. And then we will connect to 2, 0, 2, 1, 2, 2, 2, 3, and 3, 0, 3, 1, 3, 2, 3, 3. So what I just said about 0, 0, 0, 1, 0, 2, 0, 3, that means, as you can see, if it's a quadtree structure, then this is the first level, where we have 4 nodes. If we go to the next level, which means the second level, then all the first level nodes, they will be divided into quadrants, and then which means that the 0 node over here, it will be divided to 0, 0, 0, 1, 0, 2, 0, 3. So the first 0 over here indicates that indicates the location of this cell if is on the first level. So the first you can say first digit indicates the first level index. Okay, and the second digit means the location on the second level index, which means that this one is 0, and this one is 1, and this one is 2, and this one is 3. So it will be because this 0, 1, 2, 3 is is in the, like you can say, the 0 node on the first level. So it will be the 0, 0, 0, 1, 0, 2, and 0, 3. And for this one, it will be 1, 0, 1, 1, 1, 2, 1, 3, and so on and so forth. So, and as you can see, this is the like another example for the third level. So you have like much more cells, but however the order is like is still the same. So for example, like here it should be 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3, and then here is 0, 1, 0, 0, 1, 1, 0, 1, 2, 0, 1, 3. And here, as you can see, here's a link to this cell, and this cell is 0, 2, 0, 0, 2, 1, 0, 2, 2, 0, 2, 3. And this one is 0, 0, 3, 0, 0, 3, 1, 0, 3, 2, 0, 3, 3. And here, as you can see, the order, this Z order connects to this cell as the next order, next cell in line. So this one will be 1, 0, 0, 1, 1, 1, 0, 1, 1, 0, 2, 1, 0, 3. And this cell over here, it will be 1, 1, 0, 1, 1, 1, 1, 1, 2, 1, 1, 3, and then so on and so forth. So this order like is the you can say convert the two-dimensional grid into a certain one-dimensional order. And that order is like in this order. So it looks like a Z shape. So it's called Z ordering. And the other famous space filling curve is called Hilbert curve. So it was proposed in 1891. So the order defines like this. So the first node is over here, second node, third, and fourth. And if it's like the second order, the second level, then the order is look like this. And then if it's a third level, then the order it looks like this. So doesn't matter the z order of the or people call the h curve, z order or h order or h curve. So as you can see, the key idea to these two is to preserve the two-dimensional proximity, the proximity between the cells in the two-dimensional view and preserve that proximity in the one-dimensional order. So that's the reason they define this order like this. So that two adjacent cells, they are basically, well, most of the time they are connected with each other, or but they comes very close to each other in the one-dimensional order. But however, as you can still see that there are, because we convert the two dimension to one dimension, so it's basically kind of like it's guaranteed there is a certain jump from time to time. So for example, like here, as you can see, let's take a look at this one. As you can see, if when we go from 0 3 and the 0 3, the next one is 1 0. So which means that the distance from 0 3 to the nodes, for example, to this node, to the 1 2, then in this one-dimensional order, although they are in the two-dimensional grid, they are just side by side with each other. So which means that they are very close with each other. But however, they have a certain distance from 0 3 to 1 0 to 1 1, then finally to 1 2. So between the 0 3 and 1 2, in between they are two other nodes. But however, the most well, you can say maybe a bigger problem will be, for example, as you can see, this is the you can say one. Sorry, this is the 2 1. Okay, this cell is 2 1. So 0 3 and 2 1, they are also adjacent to each other. But however, in the one-dimensional order, they are pretty far away from each other, because 0 3 needs to go to 1 0 1 1 1 2 1 3, and then it will be 2 0, then finally to the 2 1. So between the 0 3 and 2 1, there's multiple like nodes in between. And of course, there are other like examples. They are farther away from each other. For example, like these 1 3 and 3 1. 1 3 and 3 1. In between here, 1 2 3 4 5. There are 5 nodes in between these two nodes. So, like I said, if you convert two-dimensional to one-dimensional, there are from time to time, there must be some jump, and those jump will cause some issues, and that issues will be mentioned later on. So, but in general, with the z order or h order, basically we can transform the two-dimensional grids to a one-dimensional order. And why this is important? Because this one-dimensional order helps us to like convert this two-dimensional to one-dimensional, so that the B plus tree can directly manage those one-dimensional order of the cells. So, and here is about the labeling. Actually, I just mentioned about the label earlier. So because the one-dimensional order needs to have a certain order. So usually we will just use the label, some labels to indicate them. So the label can be according to the Z order or H order. But here usually for the Quadtree, we will use the label that I just mentioned. For example, 0 1 2 3, 0 0 0 1 0 2 0 3. So those are what we usually call the quad key. Quad means this Quadtree, the quad of the Quadtree, and key means the key, the label. So usually we will just call it quad key. So as you can see here, this cell is 0, 0, and here this cell is 0, 1, and this cell is 0, 2, 0, 0, 2, 1, 0, 2, 2, 0, 2, 3, and here this one is 2. So if we take a look at the quadtree structure of these like management, then the original quadtree would look like this. So as you can see, the 2 is the leaf node because there are not much data over here. So it handles A and B and O. So you have A, B, O for these like the node 2 over here. But for 0 and 1 and 3, they are other children nodes. So as you can see, 0, 1, and 3, they are divided into multiple nodes here. And yeah, and that's the case. So as you can see, 3, 0, let's take a look at the 3. The node 3, we have 3, 0, 3, 1, 3, 2, 3, 3. And 3, 0 actually has been divided into 4 other quadrants. 3, 0, 0, 0, 3, 0, 0, 3, 0, 1, 3, 0, 2, 3, 0, 3. So as you can see, the 3, 0 will be like connected to its children nodes over here, and which will manage those actual data. So yeah, as you can see, for this quadtree, we have the leaf nodes on different levels. For example, here these 2 and these 4 and these 3 and these 2 and this 1 and also these 4 and these 3. They are the leaf nodes, and the leaf nodes they could be on the first level, second level, or third level. So in this case, searching on this type of traditional quadtree will spend different time to do so. Yeah, so for example, let's just take a look. For example, if I want to perform the query and that point query is in the second the node 2, then in this case the root node will directly forward to the 2, and then the 2 will just compare the data with that query, and then to answer that query, and then as you can see, it's just on the first level, so it will be very efficient. But however, if the point query is over here in the, for example, as you can see, the 3, 2, so the root node needs to forward the query to the 3, the 3 needs to forward the query to the 3, 2, then to answer that, and so it will be on the second level. But if the query is on, for example, like the 303, then the 3 node it needs to forward to the 30, and 30 needs to forward the query to the 303, and then so that you can answer the query. So the performance of that will be different from the performance of searching just till the node 2. So that's the case. So how to adjust that? With the one-dimensional order and with the label over here, we know that those leaf nodes actually follow a certain order. So as you can see, it could be from 0, 0 and to 0, 1, and then to 0, 2, 0, 0, 2, 1, 0, 2, 2, 0, 2, 3, and to 0, 3, and to 1, 0, 1, 1, 1, 2, 1, 3, and to 2, and to the 3, 0, 0, 3, 0, 1, 3, 0, 2, 3, 0, 3, and to 3, 1, 3, 2, 3, 3. So it's basically like the order of here 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on and so forth. And then so you can link. So it will be like here. Well, let's just use this quadtree structure to explain the order, so that it may be a little bit more clear to you guys. So for example, it will be 0, 0, 0, 1, 0, 2, 0, 0, 2, 1, 0, 2, 2, 0, 2, 3, 0, 3 over here, and 1, 0, 1, 1, 1, 2, 1, 3, and here is 2, and then the 2 will link to the 3, 0, 0, 3, 0, 1, 3, 0, 2, 3, 0, 3, and 3, 1, 3, 2, 3, 3. So it will be kind of like the order of these. So you just go through the leaf nodes, and then finally you can have one-dimensional order of these quadtree leaf nodes. So with this one-dimensional order, as you can see, we can use the B plus tree to manage those like those leaf nodes. And so as you can see, the order I just tried to explain to you guys, you can directly use those labels and then managed by this B plus tree. And so as you can see inside the this is the B plus tree, or this is the B plus tree managing the leaf nodes of this quadtree. So as you can see, the leaf nodes they are all the nodes that we have in all the leaf nodes that we have in the like quadtree. So it will be 0, 0, 0, 1, 0, 2, 0, 0, 2, 1, 0, 2, 2, 0, 2, 3, and so on and so forth. So that's the data that we are data that we are managing in this B plus tree, and those data they are the leaf node of the quadtree. So, and of course, those leaf nodes they were directly linked to the data they are managing like this. And as you can see, because this is the B plus tree, so how to construct this B plus tree is what we mentioned before. So you should already know that to divide the first half and second half, then you are going to use the you can say one divider over here, and here in this case you will be using the 1, 2. So if the query or if the data is above or before 1, 2, then it will send to this node, and this node will determine where the data or query should send to. Okay, so by using the index over here, for example, 0, 2, 0 matched with the 0, 2, 0, and 0, 3 matched with the 0, 3 over here. So we can so this node knows how to identify where the query or where the data should go to. So as you can see, by doing something like this, supposedly is as you can see, it's a balanced tree. So from the root node to the data to the leaf node, it has the same number of same number of path, or same number of the labels. So for example, from the root to the first label to the second label. So every time, doesn't matter which like leaf node, the performance will be the same, which is 1 and 2. So performance will be the same. So let's take a look at some some example. For example, like we use point query and window query to talk about that. So let's take a look at the point query over here. So as I mentioned earlier, if it's a point query in the 3, 2, then for the quadtree, we already know that it needs to go to the root node, and root node will know that the point query should go to the 3, and 3 knows that the point query is in the 3, 2. Then we can go to the 3, 2 and answer that question. But however, here, if it's a linear quadtree, then we can know that we first need to calculate that the P locates in the you can say in the P locates in the 3, 2. So or you can say the P the first label of the P is the 3, and then the second label of the P is the 3, 2, and maybe the third label of the P is 3, 2, 0, and so on and so forth. So we can query that with that quad key, and in the you can say the B plus tree. So we can use the 3, 2 to query with the root node, and this root node will use the 1, 2 to compare with the 3, 2, and it will know that the 3, 2 is in this half of the tree, so it will forward the 3, 2 to this node, and then with the information of the 3, 0, 1, 3, 2, and 3, 1, it knows that the 3, 2 is in this part of the node, so it will forward the query to this node, and by having the information of this node, then it should be able to know that the point query is in this 3, 2 node. So the 3, 2 node will retrieve the C and B data, and then to compare with the point query P. So that's the point query. It should be pretty easy to handle by using the linear quadtree, or you can say point query can be handled efficiently by using the space-driven approach. But however, the problem for the space-driven approach is on the window query. So as you can see, the window query over here, we have the W as the window query. It covers the 0, 1, 1, 0, and 0, 3, and 1, 2. So to execute the window query in the linear quadtree, it needs to identify the order, the coverage of the one-dimensional order for this window query. So usually you will take the like the top left corner and then bottom right corner, and to identify what are the what are the quad keys of these two corners. So as you can see, the quad key for this top left corner is the 0, 1, and bottom right corner is the 1, 2. So we know that. So in this case, we can know that the data that that could cover this window could cover the data in between the 0, 1 to 1, 2. So in this case, to answer this query, the linear quadtree will collect all the data from 0, 1 to 1, 2 in this one-dimensional order. So which means that 0, 1 is over here, and 1, 2 is over here. So which means that the window query is converted to the query to collect all the data from 0, 1 to 1, 2. So which means that all the data here containing 0, 1, 0, 2, 0, 0, 2, 1, 0, 2, 2, 0, 2, 3, 3, 0, 3, 1, 0, 1, 1, and 1, 2. So all the data over here will be retrieved to compare with this window. Right, to compare with this window. So as you can see from the geometric, so from the first order, the one-dimensional order point of view, that's the range query that we will have. But however, from the two-dimensional view, then we can see that 0, 1 is over here, 0, 2, 0, 0, 2, 1, 0, 2, 2, 0, 3, 0, 3, 0, 1, 1, 0, 1, 1, 1, 2. So that's the data. The data in these nodes will be collected and then compared with this window. From the two-dimensional view, that we can see is not so efficient because there are some unnecessary comparison, especially for example like the data in the 0, 2, 0, 0, 2, 1, 0, 2, 2, 0, 2, 3, and also the 1, 1. So the data over here and over here, they are unnecessarily retrieved and compared. But however, because you convert the two-dimensional cells to the one-dimensional order, so in this case, they are the, you can say, the necessary loss in the performance, in terms of the performance. So yeah, that's basically like the case of to support the window query by using the linear quadtree. And as you can see, it's you will suffer from the problem of the problem from the space filling curve. But however, it still have some benefits because the original quadtree it really will have a lot of influence by the skewed distribution of the data. So in this case, even though the space filling curve is not perfect, but however, by using the space filling curve, then we can achieve a balanced tree with the linear quadtree. So the performance of this linear quadtree is usually is usually still better than the traditional quadtree. Okay, so here is the summary of the linear quadtree. So mapping from the two-dimensional cells into a one-dimensional list, it allows us to use the B-plus tree. And in this case, it will be efficient in terms of the memory space because we can utilize the whole space of the disk blocks comparing to the limited fan-out in the traditional quadtree. So it's more efficient in terms of the memory space, and also the response time is also improved as well. And this type of concept of converting two-dimensional cells to a one-dimensional order can also be applied to other space filling to other space-driven approaches or space-driven SAMs. So this is a pretty pretty important design actually. And but however, of course, there are some drawbacks, some problems. So first of all, unavoidably, mapping from the two-dimensional to one-dimensional, it caused some clustering loss or layer, which means that there is a certain jump in the one-dimensional order comparing to the two-dimensional proximity. So, and this will lead to the less efficient window queries. And so this is the first drawback. And the second drawback is like all the space-driven approaches. Linear quadtree is also one of the space-driven approach, and it suffers from the object duplication. It suffers from the object duplication, which means that the window queries, if all the window query, it needs to like sort the potential results and then to remove the duplicates. And not only that, those redundancy or those duplicates will also increase the index size as well. So the problems leads to the increases of index size, decreases of SS performance, and also possible expensive duplicates removal procedure. So those are the problems of the, or you can say those are the problems for the all the space-driven approaches. So this is the linear quadtree, and still nowadays some of the database management system they implement this linear quadtree because for some cases the linear quadtree is still pretty efficient even compared to the data-driven approaches. So yeah, and later on we are going to move on to the data-driven approach.